Okay, welcome everyone. It's good to see you again after last week. So last week we were discussing about your individual projects in 1:1 meetings. So today we'll continue, we'll come back to sequential models, especially RNN, which we briefly introduced last time. I will continue with RNN, a specific version of RNN, a variant of RNN called LSTM, and then we'll look at, if time permits, I mean, we'll look at attention for RNN or sequential models first, and then if time permits, we'll also talk about transformer architectures, okay, which is a slightly different architecture, also very applicable for sequential data. Okay, so let me briefly introduce a couple of things first. First is the fact that since we discussed about projects last time, do keep in mind the timeline. It's pretty limited given that there's a couple of assignments due, including assignment 3 next week. So do plan accordingly and work on your projects. Make some progress, incremental progress each week, and you can certainly contact me and the TA whenever you're facing hurdles or if you want some extra guidance. Okay. Second thing, chat. Second thing is about assignment 3. I know we are going a little bit slow on the lecture, so hopefully today's lecture will be pretty useful for both the assignments, both the questions in the assignment 3. So potentially I'll try to drop hints or even look at the codes, the corresponding notebooks that are starter notebooks for working on both assignment question 1 and question 2. We'll look at them today. And if you have, I know some of the groups, some of the teams have already started working on assignment 3. So hopefully some questions will be clarified today. If not, do ask questions during the session, or as well as afterwards when we have our office hours. Okay. So with that, let me again mention the overarching goals. So okay, so what I want to quickly show is where we are, right? So this is just a couple of minutes of just telling you where we are. So um, we are here. We're almost midway in this course. Assignment 3 is due in about a week, basically, and I have made actually I have made a slight update to assignment 3. Just I just wanted to point it out now before I get into the material. Is it's not really, the question itself has not changed. What has changed is I made a locally available link to the same notebook that you can get from this particular link. This link in assignment question 1 goes to a third-party GitHub repository. Instead of that, I mean, in addition to that, we have a local version here. Okay, so that's linked here. And I mean, so the linked version and the versions, original version, have a slight modification, which is just regarding importing torch text. Okay, and maybe when I'll show you an example of LSTM, an example of a sequential sequence model, I'll discuss what the slight changes are. It's just it's a minor change at the import level. Okay, it's just the import has been literally 1 or 2 imports have been slightly changed. Okay. And yeah, and nothing else has changed in the assignment. Yeah. So let me come back here. So we are here at section or module 5, which is going to talk about RNNs and attention and transformers. So first step, of course, is in session 5 or module 5, we want to talk about RNNs and LSTMs and a little bit of attention. And then next, we'll talk about attention again, but in the context of transformers. Okay, transformers is just another class of models, very similar to when we introduced fully connected models or convolutional neural network models. Similarly, and today we're going to be continuing talking about RNN models. Similarly, transformers is another class. Okay, it's just again a layer-wise idea of nonlinearities, but put together in such a way that they can tackle sequential data. Okay, so when we look at the goals for last lecture or module 5 and module 6, module 5, as I said, is about RNN. So at the end of that module, or when we cover that material, when we finish that material, you would definitely want to know when prediction tasks can have sequential dependencies. Some prediction tasks may have sequential dependencies, but you can ignore the sequential aspect. Okay, sometimes, and sometimes you do want to capture the sequential aspect. For example, if you're really working with time series type of data, and you want to use deep learning models, then you want to know when to use RNNs and when not to use RNNs. And last time we briefly discussed, and I'm going to quickly recap that, is the idea about unfolding, so that you know that RNN doesn't really have a notion of an explicit memory or something like that. So RNN is really an architecture, just like a CNN architecture or a fully connected architecture that you have seen in the first two assignments, for example. Next, we'll look at a specific RNN variant called LSTMs, which was popular, or which is still popular. There are other popular variants as well, like GRU is another acronym that we will see towards when we cover LSTMs. Okay. And finally, we'll just to further ground the application direction, we want to look at, hey, what applications, at least what exists already today on the internet and elsewhere, which ones resemble sequential problems, okay, where such models can be used. Next, I don't want to discuss too much about this at this point, but the next module is about the same idea, how to work with sequential data, but introduces a new class of models, very similar. They attack the same problem, which is capturing sequential information, but the architecture is different from an RNN. Okay, so and they will also have a notion of attention for this class of architecture, very similar to attention in RNNs. Okay, which we'll discuss pretty much in the first half. So in this, if when we get to this, the goal will be to explain what is known as self-attention, and we'll look at self-attention in detail. And the second goal would be, how is self-attention accomplished, and there'll be some again keywords or specific ideas to describe this architecture. Just like you had filters and ideas like that for CNN, here there'll be some ideas for the self-attention idea, the self-attention concept, which include, these are keywords, keys, values, and queries. Okay, and then we just want to recall, there's a popular architecture called PERT. Okay, we just want to recall the key characteristics of that architecture and how pre-trained models can be used for NLP. We've already seen an instantiation of pre-trained models useful for NLP when we looked at Word2Vec and Glow or any of these word embedding ideas, right? So once you have trained or obtained word embeddings from a large corpus, then it's basically every time you come across a word or a sentence, you can always replace the words in that sentence with the corresponding vector, and then you have numeric representations. Okay, and these numeric representations can capture contextual information, which was missing when you used, let's say, one-hot encoding or bag of words and those types of representations. Okay, so that's the idea. Yeah, and since some of you have already looked at assignment 2, if you have questions, do ask on the chat or interrupt me as I cover that part of the material. So let me share my annotation. Yeah. Okay.
Hi, Professor Teja. I have a question about part 1 of the assignment. So one of the first questions says that we need to change the output.
What I'm going to do is first recap RNNs a little bit. It'll be a little bit quick, but at the same time, it's good to go.
Oopsie, never mind.
Recap the ideas because it's been a couple of weeks, and then we'll get into LSTM. Okay. So if you recall, if you recall, this okay. So just recall that the sequence of topics that we are visiting has a certain rationale behind it. First is so we saw let's say word to vec, right? So word to vec and those ideas. So we were looking at NLP, by the way. So in NLP or text processing or natural language processing, word to vec was the idea of going from symbols to numbers. Okay. And basically, this is just the idea of encoding. Okay, so we need encodings or representations or embeddings. Okay, so that was the first idea. So once you can represent arbitrary alphanumeric things, for example, in English, to actually vectors. Okay, once you have vectors, computers can just do multiplications, and once you have numbers, you can always use any machine learning idea because most of it works on numerical data, right? So that was the first idea. The second idea is, okay, now we have words as numbers. Instead of words, we have numbers or vector representations or embeddings. The second idea was how to capture sequential relationship. And this is where we have been spending a little bit of time. And here, RNNs certainly can capture sequential relationship. But there's also, the next, I guess, module will cover transformer architectures. Oh, sorry. Okay. Transformer architectures. Okay, those are the two ways to capture sequential relationships. And once you have both, you can tackle textual information or sentences or natural language in a very nice way. Okay, you just need representations of symbols, and once you have representation of symbols, as well as a way to capture sequential aspect of language. Okay, because if you just jumble the words, sentences don't make sense. Okay, so that's where we are, and in particular, we are here. Okay, about RNNs. So we looked at many different types of sequential models last time. I will, it's good to look at the slide, and you'll see that in your assignment, you are actually you are doing, for example, the starter code is actually sentiment analysis. Okay, it's actually just given a movie review, you can classify it as positive or negative. That is the starter code. Although the specific task that you've been asked to do is about language generation. Okay, given previous words or previous word, suggest the next word or next words. Okay, so that's assignment 3, question 1. And similarly, question 2 is about machine translation. Okay, it's about going from a sentence in one language to another language. Okay, and so this block diagram, these two block diagrams, should give you a sense of how inputs, outs, and the intermediate blocks, since we will be using RNNs and RNN variants in the assignment as well. This is how the block level diagram would look like. Okay, very crude diagram. These two, the one being drawn in the center, these two are how your architecture would look like. Of course, inputs are in red here and outputs are in blue, but what is it in green? Okay, and that's what we're going to spend the first half of the session on. Okay. So, I mean, I'm just doing a recap, so I'm consciously skipping a couple of slides. So the first idea, so in RNN, there's the word recurrent, and neural network is neural networks, as the name suggests. So what is an RNN? Here is a diagram of a simple RNN. The underlined figure here is a compact way to draw this RNN architecture, but this is not how the RNN architecture works. Okay, so in the sense that by looking at this diagram, you should be able to look form an equivalent diagram, which is underlined here, which is on the right side here. And that's the actual diagram of the neural network. So what does that neural network look like? It's a simple idea. So at any given point of time, you'll have an input. Let's start. Yeah, x0. You'll have an input. You'll have a box, which is this RNN box. It's going to produce an output, two outputs. Okay, it's going to produce two outputs, and it will take two inputs. But at the beginning of time, you can just say, hey, input is one of the inputs is 0. Okay, so the same block, whatever is the parameter, I'm going to reuse it. Okay, it's the same function. I'm going to reapply it, the same function. Whatever, let's say it's parameter theta. I'll reapply that function and pass it on the next input, x1, okay, and the previous output to get the new two outputs. Okay, so yeah, call it h0. Let's call it h1, and let's say this is also h0 for simplicity, but sorry, h0 for simplicity. But it doesn't have to. These two don't have to be the same, but we can, let's say we make it the same. Then this is the diagram of an RNN. So if you had a time series, so if you have a training data, so how does training data look like? So let's say I have x0, x1, and x2 as my training data. So let's put one more block here. Okay, and there's one more thing, but we don't really care about this, so let's not worry about it. So let's say my training data is x0, x1, x2, and my prediction is some y. So this is a sequential model. So the y could be, for example, the first word of the sentence that you want to predict next or something. Okay, you can do that. So the idea is you need, so this h2 is basically equal to y. Okay, so you're training for this example, x0, x1, x2, and y. The architecture, computation is basically captured here. So you pass 0 and x0, you get some intermediate things, h0, let's say h0 and h0. You pass x1, you get one more intermediate output, h1 and h1. And then you pass x2, you get h2 and let's say h2. And then the h2, let's just call it y. And you want to compare with the true y. Okay, so maybe this is y hat, and you want to compare it with true y. And that comparison could be the usual square loss or cross entropy loss or whatever on your objective. So this is the really what RNN is. And most of the time we'll spend in trying to understand what is going on in this block. Okay. And this is what we did last time. So, and by the way, the sequence can be anything. Okay, it's a sequence of images. If you're doing video processing, then sequence of frames in the video, or it could be sequence of words. And we know from embedding idea that, hey, if you give me a sequence of words, I can convert them to appropriate vectors, and then I'll just have a sequence of vectors as input. Okay, so that's this part.
Professor, I have a question.
Yeah, and this is exactly what you're saying. At any stage, so think of a stage, there's going to be an input, there's going to be an output, there's also going to be something from before, and there's going to be something from after. And from before and from after is only because that example had a previous input and maybe a next output to also, and the next step where further, a next input is going to be processed. Okay, so these are the extra arrows. Okay, nowhere is the idea of a fixed memory. Okay, so there are no numbers. So this is just a computation graph, right? So what we drew here is just a computation graph. It's just that the parameters are being reused when computation is happening, right? So use a different color. So there's some computation going on all the way up to this point. There's some computation happening all the way to this point. There's some computation happening all the way to this point. Right. So that's just one computation graph. You can actually just expand it out, and it'll just be a computation, forward computation that's happening. So now what we want to do, as I said, is the expand out the question mark. And here,
Professor?
I'm just calling it vanilla RNN, but this is one example of what can go inside the block. Oops, there is a question. Okay, let's see. Let me see.
Do you hear us, Professor?
Yeah, I mean, I can hear you now. but were you even speaking before?
Yeah, I
Okay.
tried to ask question, but yeah. Professor, I have a question with respect to the parameters. So you
Yeah.
mentioned theta is the parameter, right? So theta
Yeah.
initially given to the RNN as 0, and then later it gets
Zero. I
updated,
mean, it
right?
doesn't have to be 0, but it some initial. Yeah, it could be 0. Yeah. Later on, it'll get
0
updated. Yes.
or 1. Yes. So it gets updated, and at each cell,
Yeah.
does it get updated?
So parameters of the model are these. Okay, thetas. We have to learn those parameters using
Yeah.
backprop. Okay. But
Yeah.
if I had parameters, I'm just in this example, or in this, when I was discussing this, I was just talking about the forward pass. If you had parameters, then, and if your example happened to be, if your example data happened to be, hey, given this sequence x0, x1, x2, the outcome should be y. Let's say the the thing that I need to predict is y. Then if I know the model, then this is how the model's forward propagation will look like. Start with x0, start with some, let's say 0, if the second, for the second input, you pass it through the block. Okay, the block has parameters theta. It's just a function with theta. Okay, to taking two inputs, produces an output, pass it to the next, pass it to the next, as in like use that output h0 and the next input to again produce another output, and use that output and the next input to produce eventually something called y hat, and that should hopefully be close to y. I'm just talking about the forward propagation in this when I was explaining this. Okay, we need to learn theta, certainly, and learning theta is the same as how you would have done for CNNs or fully connected layers, right? Fully
Okay.
connected models. Yeah.
Okay.
So that would
Okay.
be just theta new is equal to theta old minus some learning rate times the gradient of the loss with respect to that theta.
Okay. Got it.
Yeah.
Hi, Professor. This is George.
Yeah. Yeah.
So the fundamental motivation of this model is, my understanding is that this mechanism that is shown on the screen has the ability to understand the sequential information of the text that it is supposed to learn, right?
Yeah, all then whatever you say, understand, that informal word, everything should be captured in this model parameters. But yeah, this is supposed to exploit sequential information, or just like time series models have. Let's say we have parametric time series model, right? Like an autoregressive moving average model, then they'll have some coefficients. Let's say it's a linear model, right? Those coefficients capture the dependency of previous information and how it relates to the next information. Similarly, these parameters theta hopefully are equivalent to understanding what was there before, so as to make the right prediction next.
Well, my question is, so according to that assumption that it is in fact able to capture, so that means that x0, x1, and x2 are sequential pieces of information as well, right? So
yes,
that is
this
a
is a
fundamental
sequence.
assumption to this model.
I mean, so we assume that x0, x1, x2 have a sequential dependency, yes. But if there are no sequential dependency, that's fine too. But it's trying to exploit, if there is sequential dependency, it's going to exploit sequential dependency.
Okay, so I mean, to make a more crude example, so if I were to read a book, some book, it doesn't matter what. So x0 is word 1, x1 is word 2, x2 is word 3. So if you break that sequence, it will learn something that is not real. But if you provide that sequential set of words, it will really learn the information about how the underlying meaning of that sequential pieces are. And that's the motivation of doing this. Input 1 goes in, it processes something, and then combined it goes to input 2. That is the mechanism. Okay, thank you.
There is some, if you're going to do some interpretation, like so hopefully George, your question will be, hopefully there'll be some clarity when we do some interpretation, when we look at LSTM a little bit, because LSTM, at least post hoc, we can interpret, hey, it's trying to remember some previous information and things like that. Okay, so but eventually whenever we say remembering information, everything has to be captured through the parameters of this model.
Okay, yeah, you know where the question came from, but okay, I think I understood the framework.
I apologize about my headphones not working earlier, but since George asked the overall context, let me come back here. So we are just trying to say, if x0, x1, x2, there was no sequential relationship. It was just three features, let's say three vectors, which is just concatenate, and it doesn't matter the order. Okay, you can, for example, in tabular data, you can always permute the rows, right? I mean, it doesn't row 1 or feature 1 doesn't have to be age, and feature 2 doesn't have to be income, right? You can flip them, and it's the same model. Here, we're really trying to exploit sequential nature of the input. Okay, word 2 follows word 1 or word 3 follows word 2. Okay. Yeah, and we are looking at RNN, so capture the sequential relationship. And I think it's a good time to also just quickly mention the example code that you have in your assignment 3, question 1. That example code, or even, that example code is basically doing sentiment analysis of movie reviews. So movie reviews are basically sentences or paragraphs, right? It's a sequence of words. So x0, x1, x2, all the way to, let's say, x100. That's a sequence of words for which you want to eventually say, hey, it's a positive sentiment or negative sentiment. So of course, you can say, hey, movie reviews, I can always jumble up the words. I don't really care about the sequential information in the reviews, and you don't have to use RNNs. You can use anything else that you know from before, which doesn't really try to exploit sequential information. Okay. But RNNs are not the only way to exploit sequential information. We've already seen, for example, a CNN-based sentiment classification or sentence classification, I think a couple of lectures ago, a couple of sessions ago. Okay. So this is exactly what's happening in that example code, a simple sentiment analysis. Yeah, let me move forward. Yeah, so I will try not to spend too much time in this in block A. But I'll do recap this diagram here in this slide, but I'll then try to go over to LSTM, because LSTM is where we want to spend much of our time on today. It's going to be it's in terms of the idea, it's the same idea. Okay, it's just what changes is this, what is inside this green box. Okay, what is inside this green box changes. Input outputs are almost, it's the same idea. Okay, it's like 2 inputs, 2 outputs. Maybe LSTMs have an extra input and output, but that's that's a detail, that is second order detail for LSTM. It's not at this point. All I'm trying to say is that we're going to look at iterate through two variations of what does this block A correspond to. The first variation is this vanilla RNN. Here, the block A is just a simple, it's just a simple linear layer, okay, followed by a specific nonlinearity, which is the tanh nonlinearity. So to recap, so let me focus on the center. So there are 3 blocks here, right? A, and A. The central A, the green block, has been expanded. We didn't write an A there, but it's basically the same A. Okay, and let's zoom in there. So what is happening? So 2 inputs, right? So you can see there's an input here, and there's an input here. Okay, we're just representing this function in a pictorial way. So 2 inputs. And let's say there are 2 dimensions. Okay, so in the sense that the input coming from like the previous processing step is a 2-dimensional vector, and input coming, which is xt, which is coming right now, is also 2-dimensional vector. So I have 2-dimensional vectors. So 2 2-dimensional vectors. That's why there's a number 2 here. So here what's happening is I'm concatenating them. So I'm just, hey, first 2 numbers and then next 2 numbers, I get a 4-dimensional vector. So that's, for example, drawn here. Some number, one more number, and one more. So once I concatenate them, I have 4 numbers. Okay. Then I'm going to pass them through a linear transformation, which, let me write it again. It's just W times that the 2 inputs. Let's call it H and X. XP, I can put P's there, but it's the same idea. And then plus P. Okay. This is a linear transformation. Okay. And then I'm going to apply nonlinearity, which is tanh. And tanh nonlinearity, I'll apply element-wise, right? Once I apply this nonlinearity, I'll get an output, right? That output is going to be 2-dimensional, okay? And so what does that mean? So W is going to be a 2x4 matrix. Okay? Because I concatenate it, so I have a 4-dimensional thing which is going into the linear transformation. But I know that the hidden output from the previous time was just 2-dimensional. So even next stage, like here, I need to pass a 2-dimensional thing as the output. So W, the number of rows I'm going to keep is 2. The number of columns I'm going to keep is 4. So that once I get a 4-dimensional input, I'm just going to make it into a 2-dimensional vector. Okay. And B again is also going to be a 2x1 vector. Okay. and then the tanh nonlinearity. And you've seen this many times in pretty much the first couple of sessions. We were looking at linear layers and fully connected neural networks. So this is exactly just one fully connected layer. Okay, that's it. And that's it. That's the entirety of A. And you keep repeating your computation here. The trainable parameters are just these two, W and B. W and B are basically the theta in my previous example. And you need to learn this theta so as to do well. Okay. And so as to do well in the sense that whatever the task is, if it was the sentiment classification task, and you will see that in that notebook, we do have, in fact, we do use exactly this RNN. So in the sense that this variant of RNN. So just to give you some idea there. So in PyTorch, this is just a specific details. NN.RNN basically does this. Okay, does computation. Okay. It does a little bit more in the sense that when you give an input, it does. I mean, generally the input is going to be the whole sequence, and so it'll do. Let's say the sequence is of length 3. In the previous example, we saw that x0, x1, x2. Then NN.RNN call will do the 3 steps. Okay, so it'll take the first input, multiply with the current parameters theta, get the intermediate output h1, and next input it'll take and process to get your h2 and then h3, and that will be the output. And we'll see the code again just to recap this. But coming back to the original idea, vanilla RNN, the simple inside that green box is just this: a single linear transformation followed by nonlinearity, and that's literally a fully connected layer, right? So we just have a fully connected layer in here. Okay. So we've discussed this last time, so hopefully it should not be super new. And here was a small code implementation. I'll not go into details of this guy because we'll look at the example starter code in a couple of minutes. And so we'll just have a look at how it's laid out there. Okay, so this is not using PyTorch. This is just a example implementation of how you would do RNN computation if you were just given, let's say, NumPy as a starting point. Okay? So, and it just describes exactly what we talked about: a linear transformation followed by a nonlinearity, and it uses NumPy functions like horizontal stacking and things like that to achieve this. Okay, and do some initialization using NumPy's objects. Okay, random objects, for example. Yeah. So this is actually part of question 1 in assignment 3, which is about building a language model. Right. In fact, question 1 is completely about building a language model. Although the starter code is not about language model, it's about sentiment classification. So there is some changes needed, and it's pointed out in the assignment 1 in that question. Sorry, assignment 3, the question 1 of what changes are needed to get to a language model. So, what is the language model here? Okay, so we have seen this language model earlier as well. If you recall, if you go back to when we started talking about introduction to NLP, we looked at a few models. One of the models was the language model, and we used Markov modeling there to build a language model. So yeah, so here I'm describing just as an example a character level language model, but it doesn't have to be character level. It can be at the word level. So what does the language model do? Okay, so given the model, so language model is just a specific application, specific name for an RNN model when it deals with, when it produces a specific object, when it produces specific predictions. Sorry. So when you have a language model, what you can do here is, what the model does is actually, it has produced some Y. The model is basically producing the probability of the next character or the probability of the next word. That's what a language model should do, given the sequence of previous words or previous characters. Okay? That's that. If the model does this, then it's called a language model. So given previous characters or previous words, if you can predict the probability of the next word or the next character, then that's essentially a language model. And of course, if you have such a gadget, such a model, then you can generate new text, because once you have a probability of what's the next word, you can sample from that and get that next word. And now you have a longer list of words, and then use a longer list of words to produce the next word and so on. Okay, so this is what you could do. Here, this is the example for if you have character level language model. Yeah, and here's the what we're going to do is actually go through the language model in terms of an RNN. Okay, so although we are talking about character level here, just think of the whole idea, is applicable to word level, and which is what will help you get a sense of how to do that for words in question 1. So let's say vocabulary is just 4 words. Apologize for just zooming in and out here. So let's say we only have 4 words or 4 characters, sorry, here, H, E, L, and O. So let's say we have one training example, H, E, L, L, and O. So this is like your X0, X1, X2, X3, and X4. It's like your, it's a starting point, X0, X1, X2, X3, X4. But from here, we're going to create multiple actual training sequences. So this, let's say, our original raw training sequence is this, from which we're going to create many training sequences. And what are they? If I give just X1 as an input, I need to predict X2, right? That's the next character. Similarly, if I give X0 and X1, I need to produce X2, which happens to be L here. Okay. Similarly, if I output X0, X1, and X2, I need to produce X3, which is again L. And if I input X0, X1, X2, and X3, the 4 characters, then I should predict the 5th character. Okay, so that's what I want to do. So that's why I said raw data and actual training examples. Actual training examples will be these 4 given a file length sequence. Okay, so here we didn't have an explicit label. Given the raw training sequence of words or characters, in our case characters, we are producing the target that we want to predict. The target we want to predict is just the next character. So that's the idea. And let's say we have, and we'll also use the idea of embedding before we talk about RNN. So again, since we have symbols, characters also are not numeric. Let's say we have an encoding for each character, and it happens to be a 4-dimensional vector. Okay, so we're not going to go into the details of how do we get these embeddings. It's just the same idea with words. Recall with words also we had embeddings. Similarly, let's say we have 4-dimensional vectors for each of the character in our vocabulary. Okay. So then the diagram for the particular example that we have looks like this. Okay, so where although there are 4 examples here, right? The figure, if you think in terms of RNN, looks like the following. Some RNN blocks. So we'll actually put 4 RNN blocks here. Although sequence length is 5, that's because the 5th output has to be O. Ideally, I want to produce O, right? And this input is L. So let me actually put the inputs first. H, E, L, and L. Okay. So given these 4, the output is O. Okay. But I also said that if I put H as an input, I need to produce L. I need to produce H, E. Right? So this is E, L. This has to be sorry about that. So E, L, and L and O. So basically so at the top you are seeing X1, X2, X3, X4. At the bottom you're seeing X0, X1, X2, X3. Okay, and I'll stitch them together as well like this. Some input, but let's say this input is 0, and some output we don't get. Okay. So this is the RNN that we're aiming for in this talk example. Okay. And since we cannot pass the characters themselves, we are saying, hey, let's pass the vectors corresponding to the characters. And that's exactly what this diagram is showing. So we have H, E, L, L, the X0, X1, X2, X3, and we hope to predict or produce vectors which are closest to the character vectors that we care about. Like for for the first guy, for when I produce H, the output should be E. When I produce H and E, when I give input as H and E, I should produce L and so on. Okay. So yeah. So here we're just seeing the numbers. In fact, the embedding that we use, since we only had the vocabulary of size 4, and we said we'll use a 4-dimensional embedding, we just happened to pick the bag of words. We have happened to pick the one hot encoding. Okay, so H just represents 1000, E represents 0100, and so on. Okay, this is just for illustration. You can use, for example, if you were really working with words, you can certainly use word-to-vec representation here, and it's actually part of the assignment 3 as well. Yeah. So any questions about this illustration here?
Hi, Tejas. So are each of those numbers there in each layer going to be the probabilities of each character that's going to come into the model?
So let me disambiguate what these numbers are. This first one is the encoding of the words, encoding of the characters. Those are external. So if you had some encoding from before, you can use them. If not, you can just use one hot encoding. So they are not really trainable. They're not doing anything here like these ones, right? They're just one hot encoding representations of the 4 characters in our vocabulary. What are these numbers? These numbers are the outputs of the RNN. Just think of this as H1, H2, H3, H4. So remember, RNN has to produce 2 inputs and 2 outputs. Let's focus on this, right? So let's focus on this guy. There are 2 edges going in, right? So this one and this one, and 2 edges going out, this one and this one. So the numbers in the green block are just saying, hey, what is the output? So it just, here the numbers are arbitrarily filled. It's just 0.1, minus 0.5, and 0.3 are just the 3 numbers, which happen to be H3. Okay. And what are these numbers? These numbers are supposed to be the scores. Okay, so remember when H3 was, if you recall, the vanilla RNN is just doing tan H of some linear transformation. So tan H output of a tan H nonlinearity produces numbers which are between 0 and 1. Sorry, between -1 and 1. But here, unfortunately, the numbers are not between -1 and 1. But these numbers are just trying to say, for example, if you want to, so here we were supposed to ideally predict L, right? So just think of these numbers in blue boxes as the scores, where you want to score for the L, for the character L to be high, and we know character L is ideally the 3rd coordinate, and so we just want the 3rd coordinate score to be high. So if you think of a 4-class classification, at this step, we just want the 3rd class to have, the 3rd class, therefore the 3rd coordinate to have a higher score. Okay. So does that clarify? So let's maybe let me ask you a question, which is, which set of numbers are you confused about? There are 3 sets of numbers, right? Top row, the central row, and the bottom row.
Professor, you are asking CJ, right?
Yeah.
I couldn't quite hear the question. Could you repeat that again?
No, I was just curious, which step are you confused about? I think you asked me what these numbers represent, right? So I'm just saying that the numbers in the blue boxes, the top row, are basically equivalent to the probability of you predicting one of the characters. Okay, so the ones in the green are what you ideally want to predict. Ones highlighted in green, sorry, the green numbers inside the blue box are the ones, those are the numbers you want to be high. Okay, those are like the scores, and you want the score for example, the letter E, which happens to be the 2nd letter in the vocabulary, and therefore the 2nd coordinate in the one hot encoding. That guy has to be high. Yeah, so these are not really probabilities themselves, because you can see the numbers are negative and positive and all over the place. You can softmax it, and then you'll get probabilities of that character.
Professor, the hidden layer numbers, right? So those numbers represents the equivalent of theta that we discussed previously, right?
No, these are not the parameters. These are the, if you apply the, so these numbers ideally should represent, sorry. Um, these numbers should represent the tan h of w of whatever the input is, like 1000 plus b. So there's also going to be, okay, I mean, in the first case, there's no previous input. Let's call it 0000. Yeah.
Right. Okay. Got it. Thank you.
Yeah. Next time there'll be some parts here and some parts here, and this will be a 4-dimensional vector, 4x1. And these are this. Sorry, happen to be 3x1. I'm sorry about that. And those are these numbers here.
No, I understood. Yeah. Thank you. Yeah, my point was, so there is a theta behind this one, which is the W and the B, which is constant across all the three. And then based on these outputs, we are not seeing that. So what we are seeing is the result of that calculation between all the, and that's why, okay, that's what I was confused about. Sorry.
Yeah. And yeah, this is just an example trying to highlight, hey, what are the vectors what are the vectors that you'll have to deal with when you build an RNN model, especially you'll have to have vectors which correspond to the output encoding. So since the output is four-dimensional here, because we want to predict one of the 4 characters, right? And so this is actually relevant to the question 1 in assignment 3, where I said, we have a sentiment classifier, so the output is negative or positive. But actually, if you want to predict the next word, then you need to change the output to be the number of words in your vocabulary. Okay, so if it's a character, let's say in this case there are 4, so that's why the output size is 4 characters. But in reality, let's say there are 26 characters, then you need to have a 26-dimensional vector. And if you're doing a language model, then the output the output dimension has to be the number of words in your vocabulary. Okay, so that's the change that you need to do, for example, in the question 1. Yeah, and although I showed you, you can get these outputs, right? Yeah, what I guess, yeah, I guess George, your confusion was, hey, there's hidden layer which is 3-dimensional. How am I getting output which is 4-dimensional? Is that the question? It can be okay. If not, I'll just explain why we got a 4-dimensional. So let's say we had 3x1 dimensional vector. To get to 4-dimensional, just apply another transformation. Okay, because at the end of the day, if we happen to choose this W to be, let's say, 3x7 dimensional, then we still need to get an output which is 4-dimensional. Right? As I said, that output dimension has to be the size of the vocabulary. Okay, and so you can have another transformation W2. Which gets you, or W prime, which gets you to 4-dimensional, W prime and B prime. Just take the hidden and transform it to these cores. Okay, and you've seen this. The last of softmax layer is needed as, depending on how much, how many dimensions that you need in the output. How many, what is the score vectors dimension?
And the size of the hidden layer, so there are 3 numbers in the hidden layer as the output that comes out to all the calculations, right? So when we say the size of the hidden layer, we are specifying the size of those the numbers in there. So or is it the fact that there are 4 elements in the hidden layer?
No, there is only a 3-dimensional vector. So H1, H2, H3, H4 are 3-dimensional. The 4 green blockers that you see is only because our example had a
4 elements. Yeah, four. Okay, yeah, okay. So what we are specifying is the number of elements in that hidden layer, number of weights in that hidden layer.
Yeah.
Okay.
Exactly, number of neurons basically. If you think of that fully of the feed-forward layer, number of neurons is 3 here.
Okay, got it. Hopefully got it. Okay.
Yeah, I mean, so we'll look at this again in the code. Maybe it'll become more clear again. So what we didn't specify finally in that diagram is what is the loss function. And I think at this point, everybody should be comfortable with cross entropy loss. So as I said, once you get scores, again, you can softmax them to get a number between 0 and 1, and you can just apply cross entropy because cross entropy loss. Because remember, for the training example, this training example, we are producing a vector which hopefully should resemble the vector corresponding to E, and E, the class E, corresponds to 0, 1, 0, 0, because E is the second character in my vocabulary. So I just happen to encode it as like this. And so I want to compare this vector with this vector. So how do I compare these two vectors? I first do a softmax transformation of the blue box at the top, these vectors, right? Do a softmax transformation, and then I have y hat, and I have y, and I can compare them using binary cross entropy, not binary cross entropy, but just cross entropy loss. Okay. Yeah, and cross entropy loss you've seen before, so I'll not spend much time there. So basically, as I said, but there is already some non-triviality, right? So first time L is input, you want the next characters to be L again, but the second time L is input, you want the next character to be O. So how is this? How can the network do that? And network can do that by by appropriately choosing W and B, hopefully such that the scores such that the scores do reflect that. Okay, so there's no magic here. So the W and B, or whatever the parameters are in this RNN, have to be tuned in such a way that when it sees two L's, when it's seeing the second L as the input, it's getting a previous hidden vector, right? The three-dimensional vector from the previous thing. So that previous hidden vector and this new input L should together with W and B help me get an O as the output. Okay, so that's what's going on. That's what we want, by choosing an appropriate W and B. Okay. So any questions here? Actually, let me quickly look at the example notebook that we have at this point, so that things will become a little bit more clearer. So let's see. Yeah. So this is the same notebook, as I said. This is the same notebook. It's linked in assignment 3. If you have seen if you have accessed assignment 3 before, this link was not there. I just added this link. It's basically a copy of the simple sentiment analysis notebook from this GitHub repository. So what has changed, just let me highlight what changed, is that I just added torchtext.legacy. Is because if you want to run this notebook, you can run this notebook currently on Colab without issues. If you were running the original notebook, it would have hit some error because torchtext has changed its underlying function. So you can't import data directly from torchtext. You'll have to import it from .legacy. Okay, so that's the only change. And here also from datasets, you just need to do .legacy. Okay, so let me actually skip some of the pre-processing and directly talk about the model. Okay? So you can see the model here. This is the RNN model. So by now, everybody should be comfortable with NN.module, extending NN.module to create your own neural network architecture. And just need to define two functions, right? Init function and a forward function. So let's look at the forward. So let's look at the init, actually. So init function. Init function initializes a bunch of things. First is the embedding layer. I mean, we're just calling it an embedding layer, but it's basically takes it takes basically the input dimension and embeds your input to an appropriate embedding dimension. So think of the input dimension to be the number of words in your vocabulary, right? So let's say so input dimension is basically the number of words in your vocabulary, because you want to one-hot encode your words here. Okay? And embedding dimension is something that you choose. Hey, for each word, how many dimensions do you want to use to embed them? So for example, if you recall word2vec, if you download from, let's say, the Google's pre-trained these representations, you would have, let's say, 300 dimensional vector. Okay, 300 dimensional vector for each word. So that's the embedding dimension. So you'll instantiate this. It's basically, hey, for each, remember input dimension is the number of words. And for each word, you just want a, let's say, 300 dimensional vector. So that's it's basically a matrix. This is that matrix that we were talking about when we were talking about encoding, when we were talking about word embeddings. Okay. So now you have that as a starting point, because the input is symbols, but you want from symbols you want to get vectors, and then you can just call nn.rnn. Okay. So nn.rnn will basically is basically that vanilla RNN that we saw. So the tanh of w comma b is the bunch of parameters when you instantiate the nn.rnn layer. Okay, and then the RNN will produce the h vector, right? So remember, if you call the RNN block, whether whether it's the first stage or whether it's the fourth stage, fourth time, it's basically it produces the h vector. Let's say it was 3-dimensional. In that example, it was 3-dimensional, right? From there, you wanna again expand it back, whatever was the h vector, back to an appropriate output dimension. So the output dimension could be, if you're just doing two-class classification, output dimension would be 2. But if you're doing language modeling, the output dimension has to be the number of vocabulary. So the number of words in vocabulary. So that's an extra fully connected layer that you are adding. So RNN will have a bunch of parameters, which is what we were referring to as theta. There's an extra bunch of parameters, which is this fully connected layer. If the hidden layer is not the same size as the output that you care about, even if it's the same size, you can always add an extra linear layer. And embedding is because if your input is not, if your input is already numbers, then you don't need an embedding layer here. But we are working with text, so you need to somehow go from a character to a vector or a word to a vector. Okay. And you can see here. So if you pass, so now let's say we created this module, and you need to define the forward function. The forward function is taking the text as the input, as in the whole sequence of words. Okay, so word 1, word 2, word 3, word 4 in this notebook. But in the example, we had a character, so HELL, 4 characters. Okay, so and you can see that here it's basically the sentence length. There's an extra thing which is batch size. I will let's not worry about batch size immediately. So it's basically, for example, if you have 4 sentences or 32 sentences and so on, you can process them together in the forward pass, right? And you must have seen this when you looked at CNN transfer learning. Okay, so let's not worry about batch size. So text is of size sentence length. Okay, so first you get the embedding. So you get the embedded vector, so the vector representations for each word in your text or each character in your text. Okay, so now because of that, it becomes you get an extra dimension. Okay, so so this sentence length, right? Say there are 4 words. So when you pass the text input, what are we passing? We are just passing the index of the words. Okay, so if I had 4 characters, HELL, H is index 1, E is index 2 in my vocabulary, L is index 3, and L is index 3. So 1, 2, 3, 3 would be the things passed in this part. Okay, 1. So those are just scalar numbers. From there, I'm getting the 4-dimensional vector for each of my words, okay, or each of my character. Okay, so that's why there's an extra embedding dimension that you get. One, so this embedded is basically will have the vectors of those corresponding characters. Okay, once you have those vectors, so remember that's how many. So this embedded, just think of it as a matrix. Forget about the batch size. As I said, ignore the batch size. So embedded would be basically a matrix. Just think of matrix where each row corresponds to the embedding of a word. So if I have 10 words, this embedded will have 10 rows. If I have just 4 words or 4 characters, then this embedding will have just 4 rows. Okay? And each row will have a vector, which is of size, let's say 4, for example, in our example before, or 300 if the word is encoded as a 300-dimensional vector. Okay? Now I'm passing this whole thing, right? This embedded matrix, which could be size 4 or size 10 or size whatever, the whole thing to the RNN block that I instantiated. Okay? So therefore, this RNN block is acting on each of the inputs in one go. Okay, so you're not calling RNN again and again and again. Okay, so because the embedded is already of an appropriate length, which is the length of this text, the RNN is already producing all the appropriate outputs and hidden vectors. Okay, so it's just the API is such that you produce all the outputs and all the hiddens at the same time. Okay, so that you just, if you call this input, so if you call it on the embedded input, okay, so if embedded is of length 4, then you'll have 4 outputs and 4 hidden vectors. Okay, then it looks like, okay, sorry, apologize. So here it looks like you only get one hidden output. So you just need to check the definition of RNN to see whether it produces, whether you get the hidden outputs of all the intermediate guys. Actually, let me take a step back. So if you recall, output and hidden are the same, right? So the output just happens to be, so that's why you're just getting a hidden at the, it happens to be a one-dimensional vector. Sorry, it just happens to be one vector, okay, instead of one hidden value at every stage, right? You're just getting one hidden vector, and that's hidden dimension. Remember, it's 3 dimensions. And output also is just 3 dimensions here currently. Now this output, you need to pass it through a fully connected layer to get to, for example, the 4-dimensional vector that we saw in the example, the character language model. So here's some extra assertion. So let's not worry about the assertion. You have to pass the, for example, the hidden. Here we are just doing language. Sorry, here we're just doing sentiment analysis. So we only care about the last output. Okay, the last output, is basically hidden. So that's why we're just actually checking that, hey, output, last output is actually the hidden vector. We're just checking that. That's what the assertion is. So you just need to take the last output and pass it through a fully connected layer, and that's going to produce 2 scores. So 1 score for positive class, one score for negative class, whichever score is the highest. That's your prediction if you just do a forward pass. But what we need to do is to learn everything. Okay, we need to learn the embedding parameters, we need to learn the RNN parameters, we need to learn the parameters of this fully connected layer. Okay, so those are the 3 things that have been learned in this script. Let me check if there are any questions at this point.
Yes. So if I could just make sure I understood it right, the input dimension is the actual word or the relative position of the word in the corresponding overall text sequence.
It's not the position of the word in the text sequence. So let's say we have, actually, I think here there are 100,000 words, I assume. So if you have 100,000 words, then input dimension is just the size of the vocabulary. So number of unique words in your whole text corpus.
Okay.
And so if input dimension is just saying, hey, how many words you have throughout your training and test data and whatever, it's the whole thing. And then when you do a forward pass, you just need to give me the indices of the words. If you have, let's say, a 5-word sentence, then the word 1 corresponds to, hey, the 10th word in my vocabulary. Word 2 corresponds to, let's say, 200th word in my vocabulary. Word 3 corresponds to 210th word in the vocabulary. So then you will just need to pass 10, 200, 210, right? Yeah.
Okay.
It's just the input dimension is just vocabulary size, if you really want to use that terminology. So just passing the word indices. From word indices, we're getting the embeddings or the word representation. That's this. Okay. And once we get the embeddings, we're just passing it through RNN. Okay. The RNN is basically doing the whole operation. The figure that we saw here. Yeah. When you call the RNN step, you're already, so this x1, x2, x3, x4 are already the embeddings. Let's say they are already the embeddings instead of these words. Okay. Instead of I hate this film, there's actually the embedding for, so what you pass in as is going to be the index for the word I, index for the word hate, index for the word this, index for the word film, whatever the numbers are. Because, and from those indices, you can get the actual vectors for these words. Vector for word 1, vector for word I, vector for word hate, and so on. Okay. So you're passing x1, x2, x3, x4 all together at once, okay, in that nn.rnn module. At once, you're getting h1, h2, h3, h4, okay, but they're just being called output, comma, hidden, okay, and then the last one is just called hidden, and so and then you're just comparing you're just doing a linear transformation of the hidden with an extra fully connected layer, and that's going to produce 2 classes, positive or negative. Whichever the class is the highest, that's your predicted class. And that's what's happening in this code, in this model. So I would suggest do spend some time on understanding what this model is doing. And of course, there's a bunch of pre-processing happening to define the vocabulary, to define, to deal with the corpus, to deal with text. And you'll not have to touch anything there to solve question 1, because the same pre-processing you would do. Yeah, so you need to pretty much change just the model, and of course the model also includes changing the output dimension.
I have another question, if I may. Right.
Yeah.
So that assert line in the forward pass, right? That is essentially finding the last H. That's what you said, right?
No, so I think you can delete this. It's just a test. It's just saying that, hey, last vector in this output matrix, it's not really a matrix, a tensor, but it was a matrix. If you ignore batch size, it's basically a matrix. Okay, output is a matrix. Why is this a matrix? I just want to, okay, let me actually, since I have this, sorry, let me go back to that picture just so that everything is a little bit more clear. Yeah, so here, just think of output as this, each row in that output is this vector, okay? So output is four rows, and each row is basically this vector, okay? And it just happens that nn.module, so nn.rnn is producing output, which is this whole collection of these 4 vectors, as well as an extra hidden output, as an output. Hidden just happens to be the last one, okay?
Why?
Actually, let me take that back.
Yeah.
Let me take that back. So sorry, I apologize. The output as the variable there actually corresponds to the green ones. I'm sorry, I'm talking about this blue ones. It's not the blue ones, it's the green ones there in that code. Okay.
Oh, okay. Output is the hidden, no. So what is the hidden layer then?
Yeah. So let me go back. Where is it? No, this one. Yeah. So this output is this bunch of these collection of these green vectors. Hidden just happens to be the last of these green vectors. Okay, and that's why this assertion is saying, hey, is the last vector the same as the hidden vector? That's all. The squeeze and all is an extra operation that you need to do, because by default, the dimensionalities may not match. Okay? So this, I think you can just verify by doing like a print of that type and print of the size and so on to just get a feel for how big they are. Okay? It's just a copy. It's just a hidden is just an extra variable name for the same information, and that's why there's an assertion. You can comment this out, it doesn't matter. So instead of passing hidden, for example, you could have just passed output, the last vector of the output, which is this, okay, as to the fully connected layer. So the green stuff passes through fully connected layer, and that's the, in that code base, it happens to be a 2-dimensional scores, right? Because you're just predicting positive or negative, and you're only predicting at the end, okay? Whereas in the language model, you will need to do multiple, you need to take advantage of all the outputs. Okay, so there's an extra step that you need to do. So you can't just do pass fully connected layer only on the last one. You should do fully connected layer on each of the outputs, and then appropriately change the loss function as well. I mean, the loss function is binary cross entropy. You just need to generalize it to cross entropy, and you need to apply cross entropy not just at the last step, but at all of the previous steps.
Professor, could you please clarify whether hidden and output, whatever we are getting out from in the code, are they the same or is it different?
Hidden is the last of the outputs. Okay, so here, don't worry. So it's a misnomer in the sense that output is not really the output of the model. It's just these green vectors. Okay, it's all actually hidden vectors. So output, just think of, it's really a bad naming here. It's just the collection of all the hidden vectors that are produced by the RNN module.
Okay, so
and hidden just happens to be the last one. Okay, when in doubt, always go back and see the documentation for RNN. It will tell you what the 2 outputs are.
Yes, Professor, could you please clarify this? So output is Y's or the heads?
No, as I said, it's hatches, okay? And once you pass it through the fully connected layer, that's the Y's.
That's the Y's. Okay, okay, got it. And one more thing. So it's just an analogy. I thought it made sense to me. So could you please go back to the slides?
Yeah.
So you see that there are like just three elements in the vector of hidden layer? Is it because there are just three unique letters?
No. You choose what is the init. It's like choosing number of neurons, right? Here we get to choose this hidden dimension. So let me tell you, hidden dimension is 3. Output dimension is 4. If you want to follow this example, by the way, this code is not about that example, but if you want to follow that example, then output dimension is 4, hidden dimension is 3, embedding dimension is 4, and input dimension is 4. It just happens to be 4 because we only have 4 words. Oh, sorry, 4 characters. Four characters in that example.
Yeah, got it. And can we also give hidden dimension as 4 here?
Yeah.
Like we can.
It doesn't have to be 3 here. It doesn't have to be 3. It can be 10. It can be 200. Whatever choice you want.
Okay, got it. Yeah. Thank you.
Yeah. Any other questions? I just wanted to spend time on this because this hopefully is familiar. You need to just work with a init and a forward function to change the model. I think pre-processing should not be an issue in the sense that you should not touch it for at least this assignment question 1. But if you want to touch it, certainly look at every what are the different objects that have been created, different variables that have been created in between. Okay, so there's a lot of variables that have been created, some of which you already know, like what's the device? It's just a variable that remembers whether you can use a GPU or not. And similarly, variables like text, the objects like text, which will have vocab. So for example, here the vocab object has 2 dictionaries. Dictionary, one of the dictionaries is saying, hey, what are the so dictionary, it's not really dictionary, it's 2 lists, which are just saying what are the first 10 words, okay? First 10 words in this vocabulary. Happens to be unknown has this index 0, bad has this index 1, the word B has index 2, and so on. Okay, so if you can print the whole vocabulary, whatever is the length of this list is the vocabulary. Instead of a dictionary, they just have a list because the index for word, the corresponding number or the numeric representation, sorry, the number for the word is going to be 0, 1, 2, whatever, up to 7 or 8 or something. Okay, so you should just explore these by printing out and so on. So I don't want to spend time on pre-processing at this point because I want to now talk about an LSTM model. And I think assignment 1 does ask about working with an LSTM. And you will see that that will probably just involve touching this line. Okay, so let's actually go back to the notes. Any other questions? Okay, so what we'll do now in the next few minutes is just focus on one variation of this RNN block. So really we're just saying, hey, previously we saw W comma B under tanh, right? Just these 3 to deal with that the block inside the block A or whatever, f theta, right? So instead of that, LSTM will be a little bit more elaborate. Whatever we're going to discuss next is just an interpretation of how the different connections, what do the different connections mean? It's just a post hoc interpretation. At the end of the day, it's just a computational graph. Okay, so some numbers are passing from left to right, some computation is happening. Okay? But we are just giving a interpretation, an interpretation to what could the computation mean. Okay, but yeah, this is that as a disclaimer. So let's start with LSTMs. So why are we looking at RNNs? I think I don't want to explain that again. Yeah. So we're going to just spend a minute on what is long-term and short-term. And it just turns out long-term and short-term, as the words indicate, is just about, hey, can the model be sensitive to information seen just in the few previous steps? Or can the model be sensitive while making the current prediction to be sensitive to information that it saw maybe 10 steps ago or 20 steps ago? Like if it's a really long sentence, if you want to predict do something for the last word, like from the last word onwards, then can the model be sensitive to things information or sorry, can model be in some sense remember, or basically the model itself doesn't remember, the hidden vector somehow captures information that happened like 10 steps ago, or which happened in the beginning of the sentence. Okay. So for example, here case A, advanced prediction models. Okay, so here advanced and prediction are useful information. Immediate preceding words are useful to maybe predict models or something like that. Instead, if you had a really long sentence or even pairs of sentences where I went to, it says I went to UIC is the previous sentence, and the next few words are I live in, and you want to predict this, and maybe this information that the information about UIC, which entered through its word embedding, is propagated through the hidden vector when trying to make this prediction. Okay, so you want that to happen. Okay. How can that happen? So in pictures, basically case A is about, hey, I want to predict something at this point. So this is just an unrolled diagram of an RNN. And maybe these two are the relevant information. It just happened to be recently, that was recent input, and therefore appropriately, this hidden vector, eventually this hidden vector may have some, dependency on them, right? Hidden vectors is just transformations of these inputs in addition to the previous hidden vectors, right? Instead of that, what if the information is a long time ago, right? So maybe x0 and x1 have information that is relevant to me making a prediction or producing a hidden vector at time t+1. Okay, so that is what we just mean by long term and short term. Okay. Yeah, that. There are some questions. I don't know if they were recent. Supriya, do you still have a question about H or?
No, I just wanted to know the terminology of it. So you
H
say
is
that
the
H
hidden
vector.
vector. Yeah, hidden vector.
Okay. Okay.
And just their transformations are the outputs. But in the code, unfortunately, we just call it hidden the outputs and then doing a fully connected transformation.
Yeah.
Yeah.
It was an old question, so it was not connected to the program that you showed.
Okay. So let's talk about LSTM. So LSTM is trying to at least trying to be helpful, trying to address or capture case B type of situations where you have a sequence and you're trying to make a prediction at let's say t+1th location or t+1 stage, and information at the extreme beginning of the stage is useful for that. LSTM is an RNN which is able to ensure that information is retained, at this hidden when you're creating the hidden vector. Okay, so maybe HT, which is maybe also passed forward. The same thing, that somehow retains that information. Okay, so how does that happen? It's not like retaining the information, right? So somehow this hidden vector or this arrow here needs to be sensitive to things that happened long time ago. Okay? So you, of course, are gonna choose the parameters such that, and are hopefully tuned using training data such that this theta happens to, be sensitive to that longer term information. Okay? Longer, vector seen long time ago. Yeah, and I guess instead of like spending too much time on this, the whole point is that vanilla RNNs seem to be unable to learn this long-term, long-range information, and you can already see one of the reasons is because there's only a single fully connected layer, and so it's really hard to see how to make a hidden vector at time t depend all the way on maybe some input x0 that happened 10 steps ago. Let's say t is equal to 10 or something. And that's why there's a new block that folks introduced called LSTM, okay, long short-term memory cells. So there's no memory. It's again, it's just a function, okay, very similar to tan h of w comma b, wx plus b, but it's slightly more involved function. Okay. Yeah, and although, there are some points here saying that, hey, this is designed to avoid long-range issue that a vanilla RNN faces, we'll see the architecture and that'll become more clear. Okay, instead of just talking about that it can do A or B or C. Okay. So let's see. So let's start with the block, and we will. And here you can already see the block inside, which is the A block, right here, is already seems quite messy. So what we're going to do is really open this block and really interpret what is going on in this computation. There are a lot of edges. There are a lot of computational steps, steps going on inside this block A, and we'll try to understand how this computational steps try to manage this long-term information. Okay, so that maybe when the hidden vector is passed to, let's say, passed to ht plus 1, maybe here, it is still sensitive to information that happened a long time ago, potentially. Yeah, and instead of a first point, I'll just make it here itself, is that instead of a single tarnished layer, for example, we'll have 4 fully connected layers. Okay, so 4 fully connected layers, and each of these parts will have their own interpretation of what they are trying to do inside the block. Okay, in terms of propagating information. So that's what we'll see. That's what we'll see next. Again, in terms of notation, yellow blocks represent fully connected layers. So fully connected layer, just one layer. Okay, one fully connected layer, basically a hidden layer. This red or pink circular nodes represent pointwise computation. So they are not layers. Okay, so a layer just means there's a w comma b involved here. Okay, that's what it means. A circle just represents pointwise operation. It could be a mathematical operation like, hey, raise everything. Remember softmax operation, raise everything to e to the power x or something, right? Something like that. And then vectors are just arrows, directed arrows. If 2 vectors are merging, it's concatenate, one below the other. And if 2 vectors are, splitting off, then it's just a copy. Okay. So now let's focus on the LSTM, and we're going to do it part by part. Okay, the whole LSTM block itself has a lot of things, so a lot of regions. So let's just focus on the one part of it, which is called the cell state. Okay, cell state. So if you see this diagram, you can see that there's actually many inputs and many outputs. In fact, instead of 2 inputs and 2 outputs, that's what we've been talking about, which is ht minus 1 xt. I mean, 2 outputs, ht and ht itself. Okay, we have an extra input output. That's just specific to LSTM itself. Okay, that's just specific to this. So that's called a cell state. Okay, just think of it as a vector. Okay, so I have a ct minus 1 vector, and it somehow becomes a ct vector. Okay, so I have ct minus 1 vector coming in, it becomes a ct vector. It's not the, it's called cell state vector. Okay, it's not the hidden vector. It's not the input vector. So it has a new name. It's called a cell state vector. Okay, and you can see that I have this vector, and it's becoming a new vector. And the way it becomes a new vector is by undergoing a couple of transformations. Okay, so as you can see, since these are pink or red circular nodes, there is some element-wise operation going on. And I'll describe these element-wise operations in a moment. So there are 2 element-wise operations going on, and that gives me a new cell state, and that's passed on to the next A block or whatever LSTM block. Okay. Yeah. So as I said, this is just a vector. It runs, I mean, again, just an explanation. It runs straight through the unrolled network. There's some couple of interactions, as I said, 2 interactions. And the cell state, the interpretation is that this is the missing block or the missing vector, which is able to, transfer information. When I say transfer information, think of just vectors, numbers, right? Numbers which appeared a long time ago, they can be transformed all the way, transferred or can come all the way to, let's say, 10 steps later and so on. Okay. Of course, there's some intermediate transformations happening. So I'll tell you when these transformations are ineffective, so that information long time ago can appear even can now. So when I say information a long time ago, just think of this as a vector, right? So let's say 3, 5, and 4. So this is a vector, and maybe I'll get a vector which is 0, 5, and 4. Okay? Which means that in the cell state, one of the coordinates be changed, for example, right? We'll talk about how it happens, and it happens using these through interactions of these two transformations. Okay. Information, if it flows along unchanged, then then this is just 3. Even though there were 2 transformations here, this could just be 3, 5, 4, and this could be 3, 5, 4, for example. Okay. Yeah. So now I'll tell you, if you really want to interpret cell state as somehow retaining or propagating information from long time ago, then there are 2 parts to it, right? So propagating information from long time ago requires basically 2 things. Either you forget some information because cell state is a fixed dimensional vector, maybe it's a 10-dimensional vector. You may want to forget some information from that vector, and maybe you want to add some information to that vector. Okay, so there are 2 parts. So we'll see how to do that. Okay, and to add and remove information, we're going to use the notion of what is called a gate. Okay, and this is again a new terminology. You'll see that this terminology called gate not just appear here, but in multiple other models. But we'll not talk about other models here. So adding and removing information, as I said, is going to be regulated using gates. So what does gate mean? Gates are basically, the idea is that and by definition, it's a gate, like really a door. They optionally let some information through. Okay, so here is an example, right? So here is an example gate. Okay, so this is a gate. So what is the gate? So you can see that the black arrows represent vectors. Okay, so a vector here and a vector here. Maybe it's going in this direction, and there's a vector here and there's a vector here. Maybe going in this direction. Okay, there are vectors which I've highlighted in red. And if you recall, this is a fully connected layer, which means that there's a W comma B involved there. A sigma on it just represents that the nonlinearity used there is a sigmoid transformation, very similar to the Tanich transformation that we have seen before. So let's actually see what it is. So we have a vector, and we have this gating process, and we get an output. Okay, and so we have the incoming vector. We have another vector, okay, which is this vector u here. Okay. Given those 2 vectors, I get an output. Okay. So what is that output? That output is basically V element-wise. So this, by the way, with a circle with a cross in between is going to be an element-wise multiplication. Element-wise multiplication with the sigmoid transformation of the other vector u. Okay. So what is happening? So let's step back a bit. We have u, which is going through a linear transformation, wu plus b. That's a linear transformation. Then I apply a sigmoid nonlinearity on it. It's just the sigmoid nonlinearity. It's not the softmax step, just a sigmoid nonlinearity. Okay, so each coordinate can become 0 or 1. Okay, so that's this block here. Let's call it u prime. Okay, that's u prime. Now I have u prime and I have v. What I'm going to do is, hey, I have a v vector. Let's say 3, 4, 3, 5, and 4. And I have a u prime vector. Let's call this v. I have a u prime vector, which is 1, 1, and 0. Let's say happens to be 1, 1, 0. Then my f of v and u is equal to element-wise multiplication. Okay, so which is element-wise multiplication coordinate. So it's 3 times 1, which is 3. 5 times 1 is 5. 0 times 4 is 0. Okay, so this is what's happening in this gate. Okay, this is what is happening with a gate. Okay, so because so basically this gate is optionally letting information through. Why is that? Because you can see that, hey, because u prime's third coordinate was 0, it did not let this 4 come to the output. Okay, and similarly, because these 2 were 1, it let information transparently through. 3 was 3, 5 was 5. Now you can say, hey, is it always the case that u prime is going to have just zeros and ones? It's not the case. Okay, so u prime could be, for example, 0.8, 0.5, and 0.1. Okay? Because sigmoid is a transformation which, given an input real number, produces a number which is between 0 and 1, right? So you can have these three numbers and things will get scaled. So 0.8 times 3 is 2.4, 0.5, 2.5, and 0.4. This is the output vector. So there's a question, what do the numbers in the vectors represent again? So the numbers in the vectors are output from some previous computation. So here, I'm going to connect it back to the cell state idea that I just introduced. So what we're trying to do here is to explain what a gate means, and then we'll come back to the bigger picture, which was that, hey, we have the cell state, which is cell. By the way, the name cell just means a block, right? We have an RNN block. We have many copies of it depending on the length of the input sequence. Okay. The state, it's really a vector that's being passed from block to block, in addition to the hidden vector and all that stuff that we saw earlier, right? So in RNN, we know hidden vector from previous thing, a new input, new hidden vector, maybe as well as the output vector or something, right? Two inputs, two outputs. Now we are saying there's going to be an extra vector which hopefully captures information from previous RNN executions, previous RNN stages, okay? So that cell state, if it's passing through block by block, some information needs to be added and some information needs to be removed from that cell state. Okay, it's just a vector. And what is that vector? It's the output of some previous computation. And in fact, it's the output of all these addition and removal steps that are going on that we'll see. Okay, so to do that addition or removal, we need to think of a mechanism which is called gating. Okay, it's like a door. You boost up some signal or remove some signal, coordinate wise, and that's what's happening here. So if you think of this V as a cell state, CT minus 1, then by using this gate, the sigma and the arrow to the top, we can actually delete some coordinates, as in like make some coordinates 0 or keep the coordinates as they whatever the values they were before. In that sense, you can actually pass on information or delete information. Okay. So let me come back to cell state actually, since we just saw what does a gate here, right? A gate, as I said, is it's basically as long as you have something like this. Okay, so you need to have a sigmoid layer. Okay, outputs numbers between 0 and 1 coordinate in each coordinate. In the U prime, for example, in the U prime we saw these are numbers between 0 and 1, right? And determines how much of each component of the V vector to let through. So V vector initially was 3, 5, and 4. If U prime is 1, 1, 0, then we leave the first two components as is and kill the third component. Kill as in like make the third component 0. And similarly, if it's if it's somewhere between 0 and 1, you may dampen the first two coordinate signal values. Like if you think of the number to be high magnitude means strong signal or something, then it's just dampening things. Okay. And if mathematically folks use in this literature, the deep learning folks use this notation, but it just you need to get the intuition. It's just trying to scale the coordinates of the V vector. Okay? Scale some numbers up. You can't scale numbers up because sigmoid's output is at most 1. You can only scale things down. So either you make some entries almost remove some entries and make them 0, or leave the entries as is. Okay. Yeah. So LSTM has 3 gates, actually 3 gates to control the cell state. So as I said, cell state, we're going to add information or remove information at in any given block. But there are 3 gates to do that. So there are 3 gates to control this information flow. Okay. So look at how to first forget information in the cell state. Okay. So how do you forget information? So forget information means we need to throw away information from the cell state. So we can do that by using a forget gate layer. Okay. So a forget gate layer is basically that's the same idea. You have a sigmoid, there's some input, there's some output, and there's some cell states CT minus 1 and some output here. Let's call it CT. It's not exactly CT, but let's call it CT prime because it will be further modified. So this input, we're going to say, hey, why don't we give HT minus 1 and XT as input to my gate. Okay, so to my gate, I'm going to give HT minus 1 concatenated with XT as input. Okay, And then I'm going to get a vector, which is between 0 and 1 because it's a sigmoid transformation, right? So it's basically W times this plus B, and then a sigmoid transformation. That's this sigma symbol here. And as I said, if some coordinates happens to be 1, then you keep that coordinates input. So it just keep that cell state coordinate value. And if it happens to be 0, you make that coordinate 0. Okay. And yeah, and there's some interpretation. This is all interpretation of the computation that's happening, by the way. So yeah, so let's say we are predicting the next word in the sense we are doing language modeling. Then the cell state may include information such as the gender of the current subject. Okay, so let's say it's the gender of the current subject. So this will be useful to predict the correct pronouns. Okay, so for example, he or she. Okay, but when a new subject is observed, so new XT happens. Okay, then you want to forget the gender of the old subject. Okay, so let's say the gender of the old subject happens to be in one of the coordinates of the cell state. Okay, this is all interpretation. It's not necessary that we're not designating any coordinate to have a gender information, but if there's gender information in one of the coordinates, then the new subject should make you forget that coordinates gender, whatever value it was, it needs to be reset. Okay, that's exactly that's an interpretation that you can do when we say we want to forget old information. So is that clear? So we have the cell state here. Using XT, we modulated or basically affected each coordinate in the cell state vector. So CT minus 1 is a vector. Each coordinate, we are changing its values in this way. Okay, so giving these two concatenated as an input to the sigma transformation. That first step is to forget information. Okay, so that's what we're going to do. That's what we did with this part of the LSTM block. There are a few more blocks in the LSTM, in this screen cell. We're going to talk about that. In fact, next we'll talk about how to add information. Recall the cell state. There is the first step, which is forget information. The second step, you can see that the symbol is plus. Okay, so we're going to add information. So we're going to do vector addition at the end of the day. This is a element-wise vector addition. So vector 3, 4, y plus a vector which is 1, 0, 0 will give you a vector which is 4, 5, 4, whatever, right? So we'll talk about adding information. Okay, so that's, I guess, adding information is the same as remembering new information. We're going to do that. Okay. So to add the information, we need to decide what information we need to add. Okay. So we need to decide what information we need to add, and then we need to actually add it. Right? So for that, we are going to define two things, two ingredients. One is an input gate. Okay. This is the second gate, and a tarnished layer. Okay, so we're going to have two things: a tarnished layer, so a yellow box, which is a tarnished layer, which is exactly the same thing that you saw in vanilla RNN. We'll also have an input gate. Okay. So input gate decides which value to update, which coordinates to update. And tanh is just the usual nonlinearity that's the core of an RNN, right? So yeah, input gate decides which values to update. Tanh just creates a new candidate vector, which is C tilde t. Let's call it C tilde t. That can be added to the cell state. So let's actually zoom in there. So we have the usual previous hidden vector, ht minus 1, and the new input xt. We're going to concatenate them together. Okay. Now we're going to pass it to two locations. One is the usual tarnished layer, which just transforms, just to the nonlinear transformation, and that will get an output which is C tilde t. Okay, and then we'll also pass this concatenate thing to another sigmoid nonlinearity. Okay, and that will call the output as little it. Okay, so this is just a vector. This is a vector. And then we'll do the transformation that we saw earlier. So an element-wise multiplication. So what it's doing is, whatever C tilde t I got, C tilde t, I'm going to do element-wise multiplication with this input gate to say, hey, which information should be retained, which information should be deleted. Okay. So if you really want notation, you can just look at this. But basically, IT is this input gate. Okay, so IT is a vector. Okay, very similar to U prime. It's going to have numbers like 0, 1, 0, something like that. Okay, so numbers between 0 and 1. Okay, it could also have 0.1, for example. Numbers between 0 and 1. And C tilde t will have numbers between, tanish transformation. If you remember, it's going to give numbers between -1 and 1. So 0, say, some numbers. Okay. The multiplication here is going to do element-wise multiplication. First row times first row, second coordinate times second coordinate, third coordinate times third coordinate. Okay. So that way you get some output here, and that's the output that's added back to the cell state. Okay. So
Professor, one question. So the tan h usually keeps the value between 0 and 1, right?
No, -1 and 1.
-1 and 1. Okay, thank you.
Yeah. So basically, from the tanish layer, we got some intermediate output called C tilde t. We are doing an element-wise multiplication with the input gates controller. Right? So input gates output. Right. So those are numbers between 0 and 1, just like the U prime stuff that we saw. Okay. And they just modulate, hey, C tilde t, some numbers we need to retain or scale down, some numbers we just leave it as it is. Once you do that, you just add it back to cell state. I haven't shown it here, but that's what you do. So in the language model example, for example, it would be add the gender of the new subject to the cell state. Okay, so for example, xt, maybe is a new subject. Okay, their information is captured in C tilde t, and the input gate is saying, hey, let's actually keep, let the gender information flow through, and it will get added to the cell state. Okay, so that's what's happening here. So if you just zoom in here, C tilde t multiplied by the input gates values gives some output, and that output is added to the cell state. What we did before was remove information from the cell state using the forget gate. Okay, so we have used this and we used it. So now we have completely changed the cell state. Okay, so that's it. Those are the two operations from going from CT to CT minus 1. Okay? And this is the core of LSTM. Everything else is just trying to account for how do I get a hidden vector output as well from here. And we'll see how to do that in a second. So these are the two steps, forgetting and remembering. Okay. Now let's focus on output. Okay, so output is just, remember the vanilla RNN had this hidden vector output. We're also going to create a hidden vector output. And not surprisingly, we want to create a hidden vector output, which depends on the cell state. Okay, because cell state hopefully retains information from a long time ago, and we'll just do a nonlinear transformation of the cell state to get to a hidden vector. Okay, so how do we do that? The output is just going to be a filtered or output is just going to be a transformed version of the cell state. Okay, and how are we going to do that? So what we're going to do is do again a simple transformation of the cell state through a tanish layer. Again, a yellow block with just tanish layer, and then we are also going to scale it with a sigmoid layer. Okay, so it's going to be an output gate. Okay, so it's a gate which decides what parts of the cell state we will output. Okay, so there's an extra gate attached which says, hey, let's first transform the cell state into something new, but we'll not directly pass that new thing as a hidden vector. We'll also modulate it using another gate, which is the output gate, okay? Which says, hey, some numbers we leave it as it is, some coordinates, and some coordinates we'll kind of set it to 0. So let's focus on that. So we're getting the okay, actually, tanish layer, right? So actually, this is not tanish layer, tanish function. I'm sorry about the notation word here. It's a function. Okay, so as you can see here in the diagram, if the tanish is a circle. Okay, it's not the yellow block. Okay, since it's not the yellow block, it's basically an element-wise transformation. So if you remember, if the cell state was happens to be 5, -1, and 3, then a tanish transformation is just tanish on these. Okay, so it's just going to scale numbers to, hey, if it's 5, maybe make it 0.9. If it's -1, make it minus 0.1. And if it's 3, make it 0.7. Tanish is just squishing the numbers. Okay, numbers could be, it's just squishing the numbers. Okay, so we do a Tanish transformation, and then what we're doing is again, doing a gating operation. So again, the gate input is always the same. Gate input is always the same. ht minus 1 concatenated with xt. Okay, we'll pass it through a sigmoid. That's what we've been doing for a gate operation. Sigmoid's output, let's call it OT. Okay, so again, OT is going to be a vector which will always have ones and zeros or things between ones and zeros. Okay, let's say 0.8 or something. Now this OT is again multiplied element-wise with the Tanish output. So Tanish output is this. This guy is the OT. Then you just do element-wise multiplication. That's this X here. Okay, so that's the gate. It's just saying, hey, so should I set some numbers, some coordinates to 0, or just leave the numbers as is? And that's exactly, and whatever the output is, that's what I'm passing it as a HT. And that's also, although there are 2 arrows to HT, it's the same thing. It's just a forking of 2 outputs. So HT is just this transformed, and then with an output gate. The transformation is just Tanish transformation, and then an output gate which says, hey, some coordinates should be set to 0, or some coordinates need not be set to 0. Okay, that's so for example, in the language model example, since we saw a new subject, we may want to output information related to the actions. Okay, so for example, output whether the subject is singular or plural, so verb can be modified appropriately, right? So yeah. So for example, if it's a plural, then verb should be something verb should appropriately consider the fact that the subject is is plural, right? So these are just interpretations that you can make given the operations of 3 gates. So actually, if you come back, right, there's a forget gate to remove information from the cell state. There's a remembering, so it will also of course have a input gate, right, that will let you add information to the cell state. And then this is the removing and adding information. So those are the 2 operations going on in cell state. And then finally a nonlinear transformation followed by an output, an output gate which modulates what should be actually output as the hidden vector. So those are the 4 parts of your LSTM. So this seems quite involved, right? So there are several gates. There are 3 gates involved. There is a core nonlinear transformation. So nonlinear are the core linear layer involved, the Tanish plus the W, B weights involved. And there's also a extra nonlinearity and extra nonlinearity involved to define from cell state what the hidden vector is. So those are the 4 parts of an LSTM. Although it's involved, this happens to work or happened to work pretty well. It was proposed a long time ago and got rediscovered and all that, and seems to work pretty well. And of course, these are all many. This is just one example of a model, right, to deal with sequential data. RNNs are just one class of models to deal with sequential data. So within that class, LSTMs are quite popular to deal with sequential data, and they perform pretty well across a range of problems. Any questions at this point?
From the tan_h function,
Yeah.
it is connected to CT, but there is no value going to the CT, right? In the fourth step, there's a tan_h function, and
yeah, it's not going back to CT. It's only to define HT. Okay, so output is only about, hey, at this point CT is already frozen at this block level. So CT, whatever we got, we just pass it to the next guy. So this, whatever we got after these 2 transformations, addition, removal and addition, CT is frozen at this point. From CT, we're just defining how to define HT.
Okay.
So the operation is given CT is the input. First do a Tanish transformation, then do an element-wise multiplication, with OT, and then you define that as HT.
Okay, but why the CT and HT not having the same values?
Yeah, I mean, you could delete this extra mechanism and say, hey, CT is itself HT. Here, yeah, I mean, so cell state, is probably about global information, whereas HT is about what should be the current prediction that you need to make roughly, right? So CT, the idea is that CT, at least in terms of interpretation, should capture some longer term information in your sequence. Okay. Whereas HT could be something very specific that you need to do now. For example, if you need to predict like a verb, whether the verb has to be modified to be plural or singular, so that's something, so you're only trying to say verb right now. You're not trying to say gender information that was contained in CT and all that stuff, right? It's not, you don't need to output that.
Okay, so
it's
CT is
just
some
extra transformation. Yeah.
Okay, so CT is some high level information which is carried, and
CT,
HT
you can
is
think of it as a global information or some sort of long-term information that is carried, that's captured through, that's the core information, and HT is just a transformation of it, which is needed now to make a prediction.
okay
So
needed
CT
for
can
the
have
next.
extra information. Yeah, CT can have more information, right, which may be useful for the next cell and so on.
Okay.
Yeah.
Okay.
So the next step and so on. So actually, I think we should take a break for about 10 minutes and resume. Okay, so let's resume at 8:03. And if there are questions, please type it on the chat. I can try to address it after the break. Okay, so let's resume. Okay, so what we did in the past 30 minutes or so was to look at the nitty-gritty details of LSTM. It's just so that you know the inner workings of how at least it's conceptualized inside. There are multiple gates, 3 different gates. There is a tarnished layer, and there's a tarnished transformation, nonlinearity, and extra nonlinearity, and there's a bunch of multiplications and additions going on. Okay, and that defines input, output, as well as the cell state, right? So,
so Professor,
any
I
questions?
have a question.
Yeah, go ahead.
So, so the information that global information that we are carrying, so CT, so
yeah.
where are we actually using that information to calculate HT?
That's in this output, right? So if you see, if you zoom in here, this is CT. This whole thing is CT, right? So that's being input here.
Yeah.
First to tarnish nonlinearity, then gets element-wise multiplied, and that's equal to HT.
Oh, that arrow was downward.
Yes, that arrow is downwards.
Okay.
That's going.
Yeah, now I understand. Yeah.
Yeah.
Thank you.
It's going this way as well as to the top. Okay. So there are other variations. So I'll try to be a little bit judicious here, because I want to also discuss a little bit on assignment 3's question 2, which has an encoder decoder architecture. So that's what I'm going to talk about next. Okay. But before that, I just want to quickly comment that just like, so what you can do is actually just do nn.rnn does the vanilla RNN operation. .lstm would do the LSTM operation, which involves everything inside the gate. So there's more parameters. And .gru is another block that you can also use. It has a slightly different architecture. We'll definitely not get into the details here, because one just, it has its own interpretation of what's going on inside the cell. At the end of the day, you have a HT, an XT, and a HT as an output. Okay, HT and HT as output. So so these are, I guess, the 3 blocks of RNN blocks that you can use. Okay. So yeah, I'll not talk about stacking, although from the diagrams it's clear that, hey, whatever the intermediate outputs are, you can have another LSTM layer on top of it, right? Where these are, for example, HTs or transformations of HTs. Yeah, skip that. Yeah, and I guess one last comment is that there's a lot of investigation on which variations are the best. Variations mean, for example, should vanilla RNN be used, or an LSTM be used, or a GRE should be used, or should I use stacked versions of these things, like this complicated stuff here. Um, uh, there's a lot of empirical work that's been done, and I think empirical work is continuing to be done to understand how these, how these can be made better and how do they work as well, interpretation. For example, just like diagnostics for CNN that we did, hey, once we trained a CNN, we want to understand how it works. Similarly, for LSTMs, there's been some attempts. We will not have time to go into how to do diagnostics for LSTM. Yeah, and again, the idea of training is exactly the way, because we just saw RNN, for example, as a layer in your NN.module extended class. So you can very easily see that the way you learn the parameters is using backprop, very similar to if you had a con2D layer or a fully connected layer or anything like that, right? So yeah, I mean, so I would say this as an exercise. I would suggest looking at this block diagram here. So this diagram is exactly the LSTM block that we've discussed, except that they are explicitly accounting for dimensions. So if cell state is 2 dimensions, okay, if input is 2 dimensions, if hidden H is 2 dimensions, then how many, like what's the input, what's the output, what's the input, what's the output? That's what's captured in this diagram. But since we've already looked at LSTM once, I would say this is an exercise that you should look at offline to get more familiar with LSTM. Insights. So now what I want to do is what's relevant to the assignment 3 question 2 in the remaining 20 minutes or so. So which is a particular application of using RNNs and in particular in assignment 3 question 2, you're looking at language translation, right? So I'll skip or I'll switch over to the code in a few minutes. But before that, I wanted to talk about that application, the corresponding application in terms of diagrams first, and then we'll switch over to the code. So I'll skip sentence classification. We've talked about sentence classification several times, including this is related to assignment 3 question 1, as well as we saw a CNN-based sentence classification classifier earlier. So we'll skip that. We'll also skip image captioning example. It's not very different from a regular these are just slides. It's not very different from a regular RNN. Okay, so the usual H0, H1, H2, Y0, Y1, Y2. The only difference is that think of it as an RNN, the vanilla RNN model that you're familiar with, except that the first input, remember in the RNN, every block has to have 2 inputs and 2 outputs, right? So first input is something like a start token, okay, something, hey, start captioning. And the first input also involves an embedding of the image. Okay, so as the name says, we are trying to do image captioning in this application. Okay? So what is an image captioning problem? The input is an image, the output is a sequence of words. Okay? So we know how to generate sequences, right? I mean, that's we saw that in the, for example, the language model. With RNNs, we are producing a hidden vector output at any time, and if we transform it, we get an output vector. And if we get an output vector, we can actually get a sequence of words or sequences of characters. We've seen that example. The only difference is that now we want to start from an image and then get to a sequence of words. Those are the input-output pairs, right? So the way we do it is use a pre-trained CNN architecture, like in this example, I guess it's VGG16 or something like that. Or ResNet 18 that you've already worked with. So you get a vector, okay, a starting vector, and you use that vector as well, at least in the first, while processing the first RNN hidden output. While using the first input and also producing the first hidden vector, you somehow use the extra images embedding vector. And once you have that, you try to produce the first word. Okay, let's say you produce the first word. You use the same word as input, next input, and then produce the second word, and so on. So you just loop. Okay, so you produce one word at a time. So word 1 is produced from the image. Okay. And then from word 1, and there's also a hidden vector that's produced on the image. The word 1 is passed, and to get word 2 and so on. I hope it's clear. So word, you generate one word at a time. You create first word, then pass it as an input, while using the previous blocks, previous RNN stages output. Both of them together will produce the second word, and so on. Okay. So that's what's happening there. Now I want to get to a third example, and this third example is going to be relevant to the assignment question, and that's why I hurried a little bit to get to example 3. Okay, and so this example is about variable length inputs and variable length outputs, and that's exactly what a natural, that's exactly what even machine translation or this translation application is about, right? You have a sentence in one language, you have another sentence in another language. The number of words in the first sentence, input sentence, for example, need not be the same as the number of words in the output sentence. Right? So that means you have a variable length input, which has sequential information, have variable length output, which also has sequential information. Okay, that's what I want to, and I want to create a model which, given a variable length input, in this case, an arbitrary sentence, can translate it. Okay, that's what we want to do in that question 2. Here in auto reply, it's the same idea, right? You have a variable length input, which is an email, and we want to produce a variable length output, which is an automatic reply. Okay, and that's what we're going to talk about. But the same idea applies to translation, which is question 2. Text summarization. So you have a paragraph or a full article, text article as an input, and you produce a shorter text. It could be variable length. It should summarize the original text. Okay, so that's a variable length output. Similarly, you can also do speech transcription, right? So you have a variable length input, which is a speech signal in some appropriately represented form, and you have a text, which is an arbitrary length depending on what the speech signals actually contain. Okay. Similarly, question answering. A question would be a certain length, an answer could be a one-word answer, for example, right? So all these can actually be trained, or such models can be trained to generate such, translations, answers, summaries, and so on, using the ideas of RNN. Okay, not just RNN, and we'll see something else next lecture, next session, which is about transformers, and they are interchange. You can use any of these models to solve these seemingly difficult to solve problems, at least from what we knew before, right? So let's talk about auto reply. Auto reply, as I said, is a feature where given an input email and response, you want to produce a response appropriately given the input email, right? So here's a version, and this is where I want to set the idea of an encoding part and a decoding part. Okay? So let's say here's a version. So I have a email which has this, let's say, hi, how are you? It's not really an email, but let's say it's a sentence. Hi, how are you is the email, let's say. And I want to produce a sentence which is, I am fine, thanks. Okay? So I need to have this pairs, by the way. In training data, I need to have the type of email I could get and the type of response I want to give. Okay. And hopefully at test time, I get some email and I'll generate an automatic output. So the way we're going to pass it, and we have seen this, at a block diagram level at the very beginning, right? When we talked about variable length input, variable length output, the way we're going to do it is we're going to have an RNN block apply again and again and again and again. We don't care about the outputs, okay, at this point. These outputs we don't care about up to some point, okay, up to we finish the whole sequence, okay. We have produced the last RNNs output, okay, hidden vector. From that hidden vector, after a linear transformation, that's what HW means, it's just a linear transformation. I want to produce that hidden vector should produce the first word. Okay, we are aiming for that. Okay, so we want to tune, of course, this W and the RNNs parameters such that I'm producing the first word. Okay. In this example, since it's called first version, I'm going to just produce, I produce the first word. I also produce another hidden vector, right? That hidden vector, I'm just directly going to transform to produce a second word. And similarly, I'll get another hidden vector, I'll transform, produce another word. So I'm not really doing, I'm not really doing any, giving any inputs here. Okay, that's why this is called the first version. But if, but the right way, and we just discussed this while talking about image captioning, is I produce the first word, and then I'm going to pass that word as input to the next RNN stage, right? RNNs always require some input and some previous hidden output, right? So I'm going to produce a previous hidden output and input, okay, and then I'm going to produce a new word, okay, fine. And then that fine word, I'm going to reuse it here, and again pass it as input, do a transformation. Hopefully it predicts thanks. I'm going to tune the parameters such as it predicts thanks, and then produce thanks, and hopefully it produces the end of the sentence token. Okay, so this part, the white part, is the white blocks. They're called the encoder stage. And the parts which have been marked in red, okay, the red blocks, G0, G1, G2, they're called the decoding phase. Okay, okay. So that's and this is called an encoder-decoder architecture. This is one example of going from a variable length input to a variable length output. Any questions about this encoder-decoder? It's just a designation that has been given to when you're only parsing the input sequence, then you call the corresponding RNN stages or the RNN blocks encoder, part of the encoder. And when you're parsing the output, right? So you need to do something interesting, because you need to pass the true word. So the true, the words that you care about as a translation, or in this case, reply, those needs to be passed as input. And at that stage, these RNN blocks are called, are together called decoder. Okay? And they may have their own parameters. Okay? The encoder will have its own parameters. The decoder can have its own parameters. Any questions here? So what I'll do is what I'll do is at this point, there is one more concept that is not super critical, but I will discuss it next time, which is beam search decoding. Okay. Once you train this model, right, you had this training data. Hey, how are you? I'm fine, thanks. You have such pairs of pairs of sentences, and train the parameters of both the encoder parameters and decoder parameters. At test time, when I give an input sequence, I need to produce an output, right? So how do I produce an output? You can just pass it. You do a forward pass, right? So while doing a forward pass, since you get a distribution over words, right? So IM is just going to be the coordinate corresponding to IM may have the highest score, for example. What you can do is create, what you can do is ensure that this at test time, when you create this output sequence, you take into account the fact that, hey, if I pick a wrong word at the beginning, like let's say, instead of IM, I pick some complicated word like machine learning, then the next word, it's kind of hard to guess the next word, because the whole response has gotten derailed, right? You wanted a multi-word response, and responses get derailed depending on the previous words that you choose. And so beam search decoding is a way to deal with this aspect of, hey, don't derail your response because at the first step, the first word that you picked happened to be a suboptimal word. We're going to talk about that next time. What I want to do is switch over to the notebook corresponding to our assignment question 2, or at least the starting point, and we'll see the encoder decoder architecture. So maybe the questions, let's look at that first. Look at that notebook first. Okay, so let me not worry about this. Yeah, so this is the notebook. It's again in the examples, and it's linked on the assignment 3 question 2, right? So this is actually a translation example, right? It also has an extra step, attention, which we haven't discussed yet. But let's actually, and so they actually do both attention and without attention. So let's look at with attention, okay? So as usual with text processing, there's going to be a lot of imports, and there's going to be a lot of steps needed to get your data. Okay, so I mean, process your data. But at the end of the day, what does your processing lead to, right? So I think some of you have already started doing this and have also faced some hurdles. At the end of the day, what do you need, right? So at the end of the day, you need a vocabulary, for each word, you need to have a corresponding index, right? So in this case, these 3 words in French, they need to have a corresponding index. Okay, so a corresponding index is a scalar number, so that in the encoder, when you pass words, the words are, words don't themselves don't mean anything. There's an appropriate embedding or a vector representation of word that's used. Okay, so very similar to the previous script that we saw. So let's actually look at the model. The model, the encoder decoder architecture is also called a sequence to sequence or seek to seek model, right? So it has 2 parts. Right? So the first part is an encoder RNN, and the second part is a decoder RNN. So let's look at the encoders initialization and a forward step. And this part should be familiar to us since we saw the previous script. So initialization is you just create an embedding. Okay, so hidden size is just the, what is the hidden size of your RNN block that you want. Input size is again, what is that embedding size that you want. Okay, so sorry, input size is the, input size here is the size of the vocabulary. Okay, so if you have 1,000 words, input size is 1,000. Okay, so first we create an embedding, very similar to what we did in the previous script, example script. And then in this example, we just created a GRU based RNN. Okay, so it doesn't matter whether it's GRU or just .RNN or .LSTM. It's just one RNN block. Okay, I mean, so it's an RNN block which is reused whatever is the length of the input sequence. Okay, if the input email or the input sentence has 15 words, then you will get basically 15 hidden vectors, and you can pick one of them or all of them depending on your application, right? Depending on application. So if you look at the forward step, we'll get an input sentence. We'll get the embeddings, if the sentence has 15 words, and we'll get 15 vectors of appropriate size. And then we'll call the RNN block, okay, and we'll get again output and hidden, and you can return both the output and hidden if you want, in the forward step if you need both, okay, and you will see that we may or may not need both. For example, if you're doing just sentiment analysis, you only needed the hidden basically or the last output vector, but sometimes you may need both. Okay. So here we're just returning both because actually you'll see that for attention you'll need the output as well, but we're not talking about attention now. So that's encoding. It's a very simple. It's just embed and then apply RNN. Right. Now let's look at the decoder. Decoder is again an extension of nn.module, and it also has so these are by the way standard class specific. When you extend a class from a base class, you need to call these steps. So now let's look at decoder, right? Again, decoder will have an embedding layer. That's because the decoder also needs to produce words, right? So let's actually go back here. Yeah, so you can see the decoder, the one in the red, they also need to produce words. And so words will be inputs. So there has to be an embedding layer for decoder side as well. So if I input a word I am, there has to be a corresponding embedded vector that I need to use to pass it to the RNN block. Okay. So there's an embedding layer, and then there's a GRU, the usual G0, G1, G2 block. Okay. So an output size is going to be again the same as the number of vocabulary, especially if you're producing a word. A word can be anything from your vocabulary, right? And so output size is the same as vocabulary size. Hidden size is something that you choose. It's just GRUs. Sorry, the RNNs sizes that you need to pick. Here they somehow just pick both input size and hidden size to be the same, but you can have different sizes there. And then finally, the output of the RNN has to be linearly transformed, right? So generally, remember, if you have a hidden vector, and we've seen this a couple of times already, you would like to do a linear transformation so that the hidden size goes to the output size, because hidden size could be 3, whereas the vocabulary size could be 1,000. So you want to go from 3 dimensions to 1,000 dimensions, for example, right? And then you want to apply those are scores. So you need to apply softmax transformation, the softmax transformation that we've been looking at. And so those are the 4 layers. And then forward step is just exactly doing that. So you get the embedding. Here it's saying, hey, apply a ReLU for the embedding. It's actually something specific here. I mean, this is not something that we've seen explicitly, but you can apply a ReLU. You can apply nonlinearity anytime. So they're applying a nonlinearity at the after the embedding, getting an embedding, and then they're applying the RNN. Okay. And then they're applying a softmax operation to the, I mean, softmax is defined here, and then the function is being applied here in the forward step, and then returning the output and the hidden vectors. Okay. So that's about it. So that's decoder and encoder. And with just this, you can actually train a sequence to sequence model. It turns out that some enhancements are useful to improve the performance. And one of the enhancements is called attention, and attention is something that we'll see next time. Okay, beginning of next time. So yeah, at this point, let me pause at this point and ask if there are any questions.
Professor, I have a question.
Yeah.
So you mentioned that these encoder-decoder based network can handle the variable size input and output.
Yeah.
But when you're defining your class these for encoder-decoder, so in your init function, you're specifying the size of your input and output. So
no, it's not a so sequence length can be anything. So if you have a sentence of 15 length, or so let's say one training example has 15 length sentence and another 15 length sentence as input, and maybe 10 length sentence as output. The second training example could have 30 length sequence as input, sequence of words as input, and maybe a 10 length sequence of words as output. Right. So that sequence length is arbitrary. But here, when we say input size, when you define this class, let's say you instantiate an object, right, of encoder object, this input size is the vocabulary size. Okay, it's not the size. It's not the size of the sequence. It's not the length of the sequence.
Yeah,
there's a vocabulary size, and this is just the size of the hidden layer. And similarly here as well, hidden size and the output size, because we want to predict. Again, as words, the output size also happens to be vocabulary size. And if you have to do translation, this output size would be the vocabulary size of your destination language. Okay? And this is something that you will do in your in the assignment. Okay, but if you're just doing auto reply, the example that we saw earlier, output size and input size has to be the same English vocabulary, for example.
Yeah, I understand. Thank you, Professor.
Yeah, let me actually, so we are already pretty much out of time. So basically, as you saw in assignment, in question 2, you need to pick a language pair. So that example is already doing French to English translation. So you just need to change the language. That's one step. That basically will help you work through how do I deal with text, how do I deal with text strings and so on, right? The second step is to reverse the language. So instead of English to French, you do French to English. Okay. You can also, it's suggested here that you should also use a pre-trained embedding. Okay, so here, in this example, here you can see that embeddings are initialized from scratch. Okay. So instead of these embeddings, which are random numbers actually, you want to use, for example, a globe embedding. Okay, so or word-to-vec embedding. In that example, in the assignment, it says use globe embedding. So try to use that. Okay, and there's an example from that repository. Okay, from an appropriate repository. And that's it. And I think the rest of the stuff is just to hey, show us some sentences, create some sentences from one model, input the sentence in the second model. Hopefully, I mean, ideal case, you should get back the original sentence, but that's difficult. So this is just the third step is just to try that out. So with that, let's, yeah.
So you're still using the encoder decoder. That's where I am. So I think step 1, I'm done. So for the second globe, you still need that, right? Encoder decoder stuff that you do in the example.
It's exactly encoder decoder. It's just that in the encoder and decoder, you can, I mean, you can use, so for the encoder part, you can use, instead of creating an embedding from scratch, which you train. So when you train the encoder, you're actually training the embeddings of your vocabulary. Okay? But Glow or Word2Vec will already have those embeddings, right? So, or I mean, not those embeddings, but you already have pre-trained embeddings, right? So instead of training embeddings from scratch, you can use those embeddings. Okay, so that this will not be a trainable layer. You'll not have a, I mean, you can also train them once you initialize them as from Glow, but the point of that step is to not use, not train embeddings from scratch for your words. Use a pre-trained embedding, in this case, Glow.
That is for the reverse model, correct?
Yeah.
Yeah.
I mean, Glow embeddings are for English. So if they have to be used on input side or output side, you just decide depending on what, when you say reverse model, whichever language, it's wherever English is present, you're trying to produce English or you're trying to input English, depending on that, you have to change the embedding. And it's the same idea, right? Here or there. Yeah.
Got it. Thank you.
Yeah. Yeah. Okay, I think we really took time. So thank you so much. And I'll see you guys next week. And folks who want to stay back can stay back and we can discuss more. Yeah, I'm stopping recording now.